Hello and welcome. The title of this video is The Most Universally Misformulated Principle in Physics. That title is not just clickbait. I really think that what I want to talk about is the most universally misformulated principle in physics. But before I get on to what that principle is, I first want to spend a good amount of time talking about the hydrostatic paradox, also known as the pressure paradox. And I'm not doing this as just a cheap tactic to increase the watch time on this video by delaying the moment where I reveal what the most universally misformulated principle in physics is. It really will be valuable to begin with this discussion of the hydrostatic paradox. So, imagine a manufacturer makes barrels with a capacity of 50 litres. Let's say each barrel is roughly spherical, so it has a height of about half a metre, and there's a small hole at the top of the barrel. Now, to test how strong these barrels are, the manufacturer does a test in which a machine presses against the inner surface of the barrel, trying to push directly outwards, and this outward force on the barrel is applied evenly throughout the inner surface of the barrel. And let's say that the total magnitude of force being applied on the inner surface of the barrel is F kilograms force. So to clarify, a kilogram force means the amount of force that is equal to the weight of 1 kilogram. And so F kilograms force means an amount of force equal to the weight of F kilograms. And what happens in this test is that F is very gradually increased until the point that the barrel bursts. And so then the question that the test is evaluating is, what is the value of F at the moment that the barrel bursts? And let's say that when the manufacturer does this test, the answer turns out to be about 20,000. So in other words, if you imagine the weight of a 20-ton object being distributed over the inner surface of this barrel, pressing outwards on this inner surface, that's the kind of quantity of force that would be needed to be able to break the barrel. And to give a sense of what 20 tons is, apparently the mass of a fully loaded coach is of the order of 20 tons. So the upshot is, the barrel is pretty strong. Okay, and now imagine that we purchase one of these barrels and fill it with water. So it's filled with 50 litres of water. Now, a litre of water has a mass of 1 kilogram, and so the mass of water inside the barrel is 50 kilograms. And now we imagine that we attach a vertical tube of arbitrarily high height to the hole at the top of the barrel, and this tube has an internal cross-sectional area of 1/3 of a square centimetre, and we slowly add water down this tube so that the water level in the tube rises. And the question is, how much water do I need to pour into this tube in order for the barrel to break? Well, the hydrostatic paradox is called a paradox because a paradox means something that feels contradictory or contrary to intuition. You see, what your intuition probably tells you is that the answer should be something roughly of the order of 20 tons of water. In other words, you need to add around 20,000 litres of water, which would mean that the column of water in the tube is about 600 kilometres high. But the thing is that a real-life experiment has been done with the quantitative details being not very far off from what I've presented here, and the amount of water that needed to be added to the tube in order to burst the barrel was not in the order of thousands of litres. It was, in fact, about 1 litre or less. And indeed, in the problem as I've set it up here, about 1 litre is what is needed to burst the barrel. So this means that the column of water in the tube has a height of about 30 metres. And so, even though there's only about 51 kilograms of water, this 51 kilograms can still provide a force on the barrel that's about 400 times its own weight. Now, the principle underlying this surprising fact is the hydrostatic pressure principle, which tells us how to calculate the amount of water pressure at any point in a body of water in equilibrium. Well, when I say water, it's actually any ideal incompressible fluid, so we ignore effects like surface tension and capillary action. And to illustrate how this principle works, let's consider a point P on the inner surface of the barrel. So the water is pushing outwards at that point with some amount of force, except that if it's literally just a single point, then the amount of force being applied at that point is zero. So instead we should be thinking about the force per unit area, which we call pressure. So how do we determine what the pressure at this point P is? Well, what we do is to ask, how far below the water level is this point? So let's say, for example, that the point P is 30.2 meters below the water level. Then, to determine the pressure at the point P, we imagine an upright prism of water of the same height, so in this case the height is 30.2 meters, and when I say an upright prism, I mean that this body of water has uniform horizontal cross-sections. And now we ask, what is the weight of our hypothetical prism of water divided by the horizontal cross-sectional area of this hypothetical prism of water? And whatever the answer to this happens to be, is precisely the actual pressure applied at the point P in our actual setup. Now, note that I haven't specified what the shape or the area of the horizontal cross-sections of my prism is. I don't need to, because whatever shape and area I choose for the horizontal cross-sections, I'll always get the same answer for this ratio of weight divided by cross-sectional area. And so, for example, if I choose my horizontal cross-sectional area to be 2/3 of a square meter, which happens to be approximately equal to the interior surface area of the barrel, then the volume of the prism is equal to 2/3 of a square meter times 30.2 meters, which comes to about 20 cubic meters, which is 20,000 litres. And so the weight of the prism of water is about 20,000 kilograms force. And this is similar to the amount of force that the manufacturers found was needed to burst the barrel. So now, dividing the weight of our hypothetical prism by the horizontal cross-sectional area gives a value equal to 3.02 kilograms force per square centimetre. So basically, each 10 metres of height contributes 1 kilogram force per square centimetre to the pressure. By the way, a kilogram force per square centimetre is also known as a technical atmosphere, which is given the symbol at, and is a tiny bit less than a standard atmosphere. So the hydrostatic pressure principle can be formulated as follows. For a body of water in equilibrium, the water pressure at a point x meters below the water surface is equal to x over 10 kilograms force per square centimetre, regardless of the shape of the body of water, and so in particular, any extra information about the volume of the water lying above the level of this point provides no alteration to the value of the pressure at this point. Now that's for water. For a different fluid, you would simply adjust this formula for the fluid pressure in proportion with the density of that fluid. So for example, for a fluid with 3 times the density of water, the pressure at a point x meters below the surface of the fluid would be equal to 3x over 10 kilograms force per square centimetre. So that's the hydrostatic pressure principle, and I will shortly illustrate how this can be seen as a consequence of the work-energy principle. Okay, now I'd like to give another example of the hydrostatic paradox that is basically exactly the same as the one that we already looked at, but from a slightly different angle. So let's say I have an upright cylindrical container with circular horizontal cross-sections of area 1 square decimetre, which is the same as 100 square centimetres. Now, decimetres are quite a nice unit when dealing with water, because a cubic decimetre is the same as a litre. Now I should also clarify, this 1 square decimeter is the interior cross-sectional area, meaning that it does not include any of the thickness of the walls of the container. And let's suppose I pour 1 litre of water into this container, so it reaches a height of 1 decimeter. And now, suppose I have a horizontal circular sheet where the area of this circle is 1 square decimeter, and I puncture a hole in this sheet of area 1 square centimetre, so the remaining area is 99 square centimetres. And now, extending up from the hole is a vertical tube with the same horizontal cross-sections as the hole itself, so the tube has an interior horizontal cross-sectional area of 1 square centimetre. And let's assume that this whole structure consisting of the punctured sheet and the tube is a single rigid object. Now, unlike in the previous setup, I'm not going to be adding any more water besides the water that's already present in the container. Instead, I'm going to put my object into the container and slowly push the object down through the water so as to gradually force water up the tube. Now let's imagine that I've pushed the object down to a level where the horizontal face of the object is 5 centimeters above the base of the container. So there's still half a litre of water below the object, but the other half a litre is now within the narrow tube. And one can calculate that this means that the height of the column of water inside the tube is 5 meters. Now, the lower horizontal surface of the object is, unsurprisingly, subject to an upwards force being exerted on it by the water. Right? You can imagine that in order to have pushed the object this far down, we will have had to press down on the object sufficiently hard to overcome the water's resistance to being forced out of the way and up the narrow tube. And likewise, once we've already managed to push the object this far down, just to keep the object in this position will still require an ongoing downward force, otherwise the upward force from the water would simply push the object back up. And so we can now ask, with how much force is the water pressing upwards on the lower horizontal surface of the object? Now, when we have an object that is partially or fully submerged in a fluid, the force with which the fluid tries to push that object upwards is called upthrust or buoyancy. And so what we're asking is, in this particular situation, what is the value of the upthrust force on the object? Now again, our intuition might say something like the following. The reason why the lower horizontal surface of the object is being pushed on by the water is because the half a litre of water in the tube is being pulled down upon by gravity, and so the upthrust force on the object is probably more or less equal to the weight of this column of water in the tube, which is equal to half a kilogram force. But now, developing this intuition a bit further, you might think to yourself, well, the area of the hole is 1% of the total area of the horizontal cross-section of water immediately beneath the level of the lower surface of the object. Now, if the hole had been much larger, say 99% of the total horizontal cross-sectional area rather than just 1%, then it's obvious that the entire weight of the column of water in the tube isn't going to be concentrated on just that remaining 1% of area where the water is in contact with the lower horizontal surface of the object. And so likewise, in our actual situation where the lower surface of the object is 99% of the total horizontal cross-sectional area, it feels intuitively reasonable that 99% of the weight of the column of water in the tube goes into pushing upwards on the lower surface of the object. And so maybe the upthrust force is equal to 99% of our 0.5 kilograms force, giving an answer of 0.495 kilograms force. There's also an alternative line of intuition as follows. Maybe the upthrust force should be equal to the weight of the amount of water that we've had to elevate against gravity to a higher position than the original water level in the process of pushing the object down through the water. In other words, the upthrust is equal to the weight of all the water in the tube that is more than a decimeter higher than the base of the container, because the original water level was 1 decimeter above the base of the container. Now, simple geometry tells us that the volume of water that is higher than the original water level is equal to the volume swept out by the horizontal face of the object during the process of pushing the object down through the water. In other words, in intuitive terms, it's the volume of water that the horizontal face of the object has had to come into direct contact with and physically push out of the way in order to descend 0.5 decimeter down through the water. So that's equal to the area of the horizontal face, namely 99 square centimeters, times the depth of water that the horizontal face has sunk through, namely 5 centimeters. And this gives a volume of 495 milliliters, which has a weight of 0.495 kilograms force. And so again, this line of intuition suggests that the value of the upthrust should be 0.495 kilograms force. So I've given 2 intuitive justifications for an answer of 0.495 kilograms force. But as you can already see, this situation is actually basically identical to the previous setup involving the barrel, and so the hydrostatic paradox is again going to be at play. So for the correct solution, as we've already said, the height of the column of water inside the tube is 5 meters, and so the hydrostatic pressure principle tells us that the water pressure at each point on the lower horizontal surface of the object is equal to 0.5 kilograms force per square centimeter. And please note that this is precisely equal to the weight of the column of water inside the tube divided by the horizontal cross-sectional area of the tube. And now, multiplying this pressure by the area of the lower horizontal surface of the object, which is 99 square centimeters, we get that the force that the water exerts on the lower horizontal surface of the object is equal to 49.5 kilograms force. So this is 100 times larger than what our intuition might suggest. And please note again that the entire body of water in the system is just 1 kilogram of water, and yet the water is exerting an upthrust force of almost 50 times the weight of a kilogram. Now, incidentally, if you weren't aware of the hydrostatic pressure principle, you could also determine what the upthrust force should be using the work-energy principle. You see, what we can do is to imagine pushing the object further down through a very small distance that we'll call dx meters, and we can ask, by how much does the total gravitational potential energy of the water in the system increase during this process? Well, the net relocation of water that takes place during this process consists of taking the part of the water that the object's lower horizontal surface has to sweep through in the process, and raising that part of the water by a distance of about 5 meters to bring it to the top of the column of water inside the tube. Now, the weight of this part of the water is equal to dx times 9.9 kilograms force, and so the increase in the total gravitational potential energy of the water in the system is approximately equal to this weight times 5 meters, which works out as dx times 49.5 kilogram force meters. And this approximation tends towards 100% accuracy in the limit as dx tends to 0. But now, by virtue of the work-energy principle, this increase in gravitational potential energy is precisely the negative of the work done by the water on the object in seeking to resist this descent of the object through the distance of dx meters. And now work is displacement times force. And so what this gives us is that the downwards distance dx meters times the upwards upthrust force that the water exerts on the lower horizontal surface of the object is equal to the change in gravitational potential energy that we already calculated. And again, the equation that I've written here tends towards 100% accuracy in the limit as dx tends to 0. And so the conclusion is that the upthrust force is equal to 49.5 kilograms force. Okay, so in summary, our intuition said something like the upthrust force should be roughly equal to the weight of water that the object had to force up the tube in order to be pushed down to its current level. But the truth is that the upthrust force is about 50 times the entire weight of all the water that there is. And so a simple way to summarize the difference between the intuition and reality is our intuition says that the water that the object had to push out of the way fights back with a force equal to its weight. However, the reality is that the column of water inside the tube fights back according to its pressure, not according to its weight. And this pressure is determined by the height independently of the area of any of its horizontal cross-sections. And now I'd like to give one further illustration of the hydrostatic pressure principle and how it can mismatch with our intuition. This is going to be a problem that I've actually presented already in another video, but I didn't present the solution there. So here's the problem. We start with a tub of water of interior horizontal cross-sectional area 10 square meters, inside which is floating an empty tub of horizontal cross-sectional area 9 square meters. We make a note of both the water level and the level of the bottom of the inner tub. And now, into the inner tub, we place a mass, and we observe both the rise in water level, which will denote R1, and the drop in height of the inner tub, which will denote D1. Once again, the outer tub has cross-sections of area 10 square meters, and the inner tub 9 square meters. And now we have another tub of water whose interior horizontal cross-sectional area is 100 square meters, inside which is floating an empty tub of horizontal cross-sectional area 99 square meters. So note that both in this case and in the previous case, the difference in cross-sectional area between the inner tub and the outer tub is 1 square meter. Now again, we make a note of both the water level and the level of the bottom of the inner tub. Now, into the inner tub, we place the same mass as before. And again, we observe both the rise in water level, which will denote R2, and the drop in height of the inner tub, which will denote D2. And now the question is, how does the rise in water level compare between the two cases? And how does the drop in height of the inner tub compare between the two cases? As I say, I've asked this exact problem in another video, but I didn't give the answer there. Now, if you like, you can pause the video and try to work out the answer. So again, our intuition might say, since the same weight has been added to the inner tub in both cases, the weight of water that the inner tub has had to push out of the way to get to its new lowered level must be the same in both cases. And more precisely, what this would mean is that the volume swept out by the bottom surface of the inner tub in descending from its original level to its new level is the same in both cases. So in case 1, this volume is given by 9 square meters times D1, and in case 2, this volume is given by 99 square meters times D2. And so, if the two volumes are the same as each other, then that would mean that the ratio of D1 to D2 is 11 to 1. Now, basic geometry tells us that this volume in case 1 is equal to 1 square metre times the rise in water level, R1, because 1 square metre is the cross-sectional area of the gap between the inner and outer tub. And likewise, this volume in case 2 is equal to 1 square metre times R2, because again, 1 square metre is the cross-sectional area of the gap between the inner and outer tub. And so, the volumes being equal means that the ratio of R1 to R2 is 1 to 1. In other words, the same weight being placed into the inner tub leads to the same rise in water level because the cross-sectional area of the gap between the inner and outer tub is the same in both cases. So all of this is what your intuition might say, but now let's solve this properly using the hydrostatic pressure principle. So the first thing to note is that in both cases, before the object is placed into the inner tub is floating, so it's in equilibrium, and so by Newton's first law, the upthrust force exerted by the water on the bottom surface of the inner tub is equal to the weight of the inner tub. And then, again in both cases, after the object is placed into the inner tub is still floating, and so by Newton's first law, the upthrust force exerted by the water on the bottom surface of the inner tub is equal to the total weight of the inner tub and the object that has been placed inside it. And so, since the same weight has been added in both cases, it follows that the increase in upthrust force is the same in both cases. Now, in case 1, the increase in upthrust force is equal to 9 square meters times the increase in water pressure at the bottom of the inner tub, and in case 2, the increase in upthrust force is equal to 99 square meters times the increase in water pressure at the bottom of the inner tub. Now, the hydrostatic pressure principle tells us that water pressure is proportional to depth below the water surface, from which it follows that an increase in water pressure must be proportional to the increase in depth below the water surface. In our case, as the inner tub goes down and the water level goes up, the sum of those two changes is what tells us the increase in depth of the bottom surface of the inner tub below the water level. So this increase in depth in case 1 is d1 plus r1, and in case 2 it's d2 plus r2. And so we have that 9 times the sum of d1 and r1 is equal to 99 times the sum of d2 and r2. And now at this point, let's note that there was one detail in the wrong solution that was actually correct, namely, basic geometry tells us that 9 square meters times d1 is equal to 1 square meter times r1, and 99 square meters times d2 is equal to 1 square meter times r2. And so, substituting into our equation that r1 is 9d1 and r2 is 99d2, we get that 90 times d1 is equal to 9,900 times d2, and so the ratio of d1 to d2 is actually 110 to 1, not the 11 to 1 that our intuition had suggested. And then for the ratio of r1 to r2, since r1 is equal to 9 times d1 and r2 is equal to 99 times d2, and the ratio of d1 to d2 is 110 to 1, it follows that the ratio of r1 to r2 is 990 to 99, which simplifies down to 10 to 1. So remember, our earlier intuition was that since the same weight is being added in both cases, we should have the same volume of water getting pushed out of the way by the bottom surface of the inner tub, and that's why we concluded that R1 is equal to R2. But in actuality, the volume that is swept out by the bottom surface of the inner tub in descending from its original level to its new level is 10 times greater in case 1 than it is in case 2, even though the same weight is being added in both cases. So again, in summary, we have an intuition that says that as water is displaced against gravity by the submersion of an object into the body of water, the upthrust force through which that displacement of water seeks to fight back is equal to the weight of this displaced part of the water. But this intuition failed us here. The hydrostatic pressure principle tells us that that is not the correct way of thinking about things. Now, I should say, some of you may have tried to solve this problem using a slightly different version of the wrong intuition that I've just described. You may have thought that the amount of water that we should regard as having been displaced against gravity is more than just the volume swept through by the bottom surface of the inner tub, because as the inner tub pushes water out of the way, that water also has to elevate the water already present between the inner tub and the outer tub. And so you might think that overall, the body of water that has been displaced against gravity is the entire column of water lying within the gap between the inner and the outer tub. And so the upthrust force being exerted on the inner tub is equal to the weight of that entire column of water. In that case, you would conclude that R1 plus D1 is equal to R2 plus D2, which would then mean that the ratio of D1 to D2 is 10 to 1, and the ratio of R1 to R2 is 10 to 11. Now, it's actually not hard to see that this reasoning should be wrong, because if it were correct, then for an object in a vast ocean, if the object is submerged to more than an infinitesimal depth, then the upthrust force on the object would be infinite, which is obviously nonsense. But in this particular problem, you can see that this wrong answer is quite close to the other wrong answer, and it is of course still a very long way off the correct answer. Incidentally, the difference between this wrong answer and the other wrong answer is exactly the same as the difference in the previous problem between saying that the upthrust force is 0.5 kilograms force and saying that the upthrust force is 0.495 kilograms force. And all of these wrong answers, along with the equally wrong idea that we needed about 20 tons of water to burst the barrel, all of these wrong answers are fundamentally built on the idea that the elevated height or the displacement of part of the water in a system leads to the exertion of a force whose magnitude is equal to the weight of that elevated or displaced part of the water in the system. Okay, but now something interesting happens if you search for the hydrostatic paradox on Wikipedia. So it seems that at present, the only English Wikipedia page specifically dedicated to the hydrostatic paradox is the simple English Wikipedia page. And when we go to that page, we get a description of the paradox with a nice diagram illustrating the point. And then further down, we get this rather interesting statement. The hydrostatic paradox is based on Archimedes' principle, which states that an object immersed in a fluid is buoyed up by a force equal to the weight of the displaced fluid. Wait, I thought the whole point of the hydrostatic paradox is to say that that's the wrong intuition. The force exerted by water is not equal to the weight of a displaced or elevated part of the body of water. And this issue is in no way specific to the simple English Wikipedia page. If you look up pretty much any statement of Archimedes' principle, also known as the law of buoyancy, whether it's at middle school level, at high school level, at university level, or in pretty much any other setting, it will say something like the following. When an object is partially or wholly submerged in a fluid, the fluid exerts an upthrust force on the object, or buoyancy force on the object, whose magnitude is equal to the weight of the fluid that the object displaces. Now, you might see all kinds of subtle variations in the exact phrasing and grammatical construction, but what you will always see is this idea that the amount of upthrust force is equal to the weight of displaced fluid, and it will be stated without any caveats besides perhaps some contextually obvious ones, such as that the system is in equilibrium and the fluid is an ideal fluid with uniform density. And quite often, you'll also see an application of Archimedes' principle to floating objects that is phrased something like as follows. When an object is floating in a fluid, the object displaces an amount of fluid whose mass is equal to the mass of the object. Again, there might be subtle variations in the exact phrasing, but the key point is that the weight of displaced fluid is equal to the weight of the floating object. But again, that way of thinking is precisely what led us to the wrong solution to the last problem that I presented. And moreover, you can easily have situations in which a floating object weighs more than the entire body of fluid that it's floating in. And these situations are sometimes referred to as a battleship floating in a bathtub. And you can do a simple demonstration of this in your own home if you have stackable plastic cups, and I have a short video illustrating this. Now, I think students are typically first taught Archimedes' principle at about age 15 or 16, and when I first encountered Archimedes' principle, probably as a 15-year-old or thereabouts, I think my first thought was, what exactly is meant by the weight of the displaced fluid? And I probably had a subconscious, or perhaps conscious, sense that this sentence is presupposing a level of clarity of understanding about the behaviour of fluids that was greater than my own level of clear understanding. And even the word displace itself, just as a word in English, is somewhat advanced to be assuming for general 15-year-olds to have a fluent familiarity with. To displace an entity means to force that entity to relocate itself somewhere away from its original place. And it's not necessarily a word that children and young teenagers will encounter all that often. Now, of course, it's true that in science education, we expect students to be willing to learn technical scientific terms lying outside their day-to-day vocabulary, right? There are terms like kinetic energy in physics and covalent bonds in chemistry and osmosis and partially permeable membrane in biology, and students in the respective subjects are expected to learn, to a suitable level of precision, the meanings of these terms and their applications. But in our case here, when it comes to the teaching of Archimedes' principle, the verb displace is not generally treated as its own technical term with a scientific definition that the students are expected to memorize and be able to explain. So I'd like to itemize a list of 3 problems with the conventional formulation of Archimedes' principle, and I'm going to list these problems in order of increasing problematicness. But this order is also logical in the sense that each problem kind of builds on the previous one. So the first problem is that there is a mismatch between how, on the one hand, the sentence presents itself as if it's a quantitatively precise statement, and yet, on the other hand, the actual content is not precise in its wording. Yes, the reader has an intuitive sense that, qualitatively speaking, there needs to be some displacement of fluid to make way for the object becoming partially or wholly submerged in the fluid. But there are numerous ambiguities as to how one would define exactly which part of the fluid in the system, or even just exactly how much of the fluid in the system, constitutes the displaced fluid. And so, the consequences of this mismatch between what the sentence markets itself as being and what the sentence actually delivers are as follows. Firstly, as I've already loosely hinted at, the sentence is likely to be somewhat intimidating for students. If you can tell that this is meant to be a quantitatively precise law, and yet you don't understand the quantitatively precise meaning, then obviously the deficiency lies with you and your understanding. Secondly, as I've already indicated, the sentence allows contradictory interpretations. There are different ways in which one could quantify the phenomenon of the displacement of fluid, and thus pretending that the wording of the sentence is clear obscures the fact that different interpretations of the wording genuinely are different and give different answers. And of course, just drawing a diagram to illustrate the idea of displaced fluid does not solve this problem. If anything, it just makes it worse. And this nicely leads into the third consequence of this mismatch between marketed and delivered precision, which is that it facilitates the illusion of explanatory depth. I'll try and justify my argument here in more detail shortly, but the illusion of explanatory depth is essentially the idea that as we increase in familiarity with some procedure, such as the procedure of invoking the statement of Archimedes' principle within the task of constructing a solution to a physics problem, we eventually feel like we've gained a complete and logically sound understanding of why the procedure delivers successful results, even if in reality we haven't. Okay, and now for the second problem. I said when describing the first problem that this statement of Archimedes' principle uses the language of an imprecise, intuitively defined heuristic concept and presents it as though it were something scientific and precise. But even the intuition that is suggested by this statement of Archimedes' principle is itself a wrong intuition, as we've amply established. When you picture the idea of fluid that has been displaced by the object as the object descended into the fluid, whatever you're imagining as being the displaced part of the fluid will not necessarily have a weight that is equal to the upthrust force. And this leads into the third problem, which is there is no possible interpretation of the verb displace such that when the actual grammar of the sentence itself is understood as written, the statement is a correct statement. So the point I'm making is that if the sentence is phrased as being that the upthrust force is equal to the weight of the fluid that the object does something to, or the weight of the fluid that is somethinged by the object, or simply the weight of the somethinged fluid, then this means that the entity whose weight is being declared to be equal to the upthrust is a definite body of fluid that is characterized by the description of being somethinged by the object. That's why we have the definite article, the, in front of fluid that the object displaces, or fluid displaced by the object, or displaced fluid. The point is that any rule that says that the upthrust force is equal to the weight of some part of the fluid present in the system must be wrong, because we've already seen that the upthrust force can be greater than the entire weight of all the fluid present in the system. A body of fluid can exert a greater upthrust force than its entire own weight. So this contradicts the idea that the upthrust force is equal to the weight of the part of the fluid that is deemed to have been displaced, whatever that means. But you might be wondering, if the law of buoyancy is so universally formulated in this clearly misleading and frankly incorrect manner, then how come everything works? As in, engineers working in various fields of engineering successfully do calculations of buoyancy forces all the time, and these same engineers, if you were to ask them to explain their understanding of the law of buoyancy, would most likely express it in precisely the manner that I've just proved to be problematic, to put it mildly. So, what's going on? I think the answer is this. When we learn a principle in physics or any of the other sciences, what usually happens is that we're given a statement of the principle, such as the statement of Archimedes' principle that we're discussing now, and then we're often shown some kind of mathematical or conceptual derivation of that principle, followed by a number of worked examples of how to actually perform calculations involving that principle or solve problems using that principle. So even though the statement of the principle itself is often presented in a way as if to suggest that that statement is a complete self-contained statement of the principle, no educator will actually rely on just that statement alone as the means of causing the students to gain a good grasp and understanding of the principle. And so people are taught the supposed statement of Archimedes' principle, but they're also shown worked examples of how to do calculations or solve problems using Archimedes' principle, and they're also often shown a so-called derivation of Archimedes' principle from the hydrostatic pressure principle, where again, the thing that this derivation actually derives is the correctness of the scheme of buoyancy calculations that you see in the worked examples. Well, to be a bit more precise, in high school, this derivation usually is just done for the case of an upright prism-shaped object, and then you might be told that the general case requires university-level vector calculus. But even just this prism case is enough to give a sense of what it is that you're actually calculating in the place of what the original statement misleadingly calls the weight of the displaced fluid. And so ultimately the point is this. Once you've seen and worked through a broad enough range of examples, and especially if you've seen a nice simple derivation of the correctness of what you're doing in those worked examples, the way your mind works is that you will pick up clearly how to do correct calculations involving buoyancy, regardless of how clear or precise or accurate the original statement is that you were taught for the law of buoyancy. Okay, so at this point you might be thinking, well, if the education system still ultimately correctly teaches what the law of buoyancy is, but just through the indirect means of starting off with a slightly inaccurately worded statement, but then following that up with examples or derivations that make clear how to correctly apply the law of buoyancy, then ultimately there's no problem, because ultimately the students won't be under any misconceptions about the physics of buoyancy. Well, here's the thing. When I was shown the derivation and worked examples, I could see from these how I would formulate what the law of buoyancy is as it is actually applied at the level of doing calculations and solving problems. In other words, I could see how to formulate what the law of buoyancy is practically speaking, and I'll go on to explain this shortly. But what I still felt unsure of, and what certainly does not come through in the derivation that one is shown, is how the value of weight that we compute when we do these buoyancy calculations actually corresponds to the weight of the fluid that the object displaces. I understood why the calculations that we're performing are the correct calculations for working out upthrust force, but I didn't understand how these calculations correspond to the actual statement of the law of buoyancy that we're taught. It was only later on that I realized that the weight that we're computing can be greater than the entire weight of all the fluid in the system. So as I say, I was conscious that I didn't understand how the calculations that we're performing correspond to what we're taught as being the statement of Archimedes' principle. But I think that for most people, one of two things happens. Either they don't get shown a broad enough range of examples, and thus they don't acquire the ability to do general buoyancy calculations correctly, or they do pick up how to do the correct calculations in general, but they subconsciously acquire the assumption that the phrasing of Archimedes' principle that they were taught is a precisely worded, accurate representation of the scheme of calculations that they're performing when doing buoyancy calculations. So even though this latter group of people may have seen enough examples to know how to do the correct calculations, they have not seen the kinds of examples that strikingly highlight the mismatch between these calculations and the conventional phrasing of Archimedes' principle. Of all the people who are experienced in using Archimedes' principle and teaching Archimedes' principle, I think that only a fairly small minority are actually aware that the fluid whose weight we calculate when applying Archimedes' principle is a body of hypothetical fluid rather than a portion of the actual fluid in the system. And so this is where the illusion of explanatory depth comes in. Because a person is so used to phrasing the law of buoyancy in the manner that I've been describing, while at the same time applying the correct scheme of calculations for working out buoyancy, the person comes to subconsciously adopt the perception that it is an immediately and trivially clear fact of geometry that the quantity of fluid whose weight they are calculating is the same quantity as the quantity of fluid that has had to make way for the object as the object gets partially or fully submerged in the fluid. Now, as I've said, it's not even entirely clear how one defines the quantity of fluid that has had to make way for the object, but however you define it, it's not the same as the quantity of fluid whose weight is equal to the upthrust force on the object. And so, the person who I'm describing, who I believe to be representative of a very, very large number of people, really does believe something incorrect about fluids, even if the opportunity for their misconception to become manifest is fairly unlikely to ever arise. And so I'm arguing that this is not just a pedantic issue about technically correct semantics. Okay, so what is the correct formulation of Archimedes' principle? Well, we can phrase it as follows, and then I'll explain more precisely what is meant. When an object is partially or wholly submerged in a fluid, the fluid exerts an upthrust force on the object, or buoyancy force on the object, whose magnitude is equal to the weight. Okay, so far the sentence is exactly the same as before, but now, as for the rest of the sentence, the magnitude of the upthrust force is equal to the weight of fluid that would fill the submerged volume of the object. So this is not saying that the upthrust is equal to the weight of a part of the body of fluid that is actually present in the system. Instead, it's just saying, whatever your fluid happens to be, so for example, let's say the fluid is water, you need to ask, how much water would we need in order to fill a volume equal to the volume of the submerged part of the object? And whatever the weight is of that amount of water that we would need, that is the value of the upthrust force being exerted by the actual water in the system on the object. So let me try and illustrate what this sentence is saying. Suppose we have a body of water and an object that is partially or wholly submerged in the water. Now, we can identify what the water level is, and we can imagine a flat horizontal plane at this water level. In other words, we're thinking about the horizontal plane in space that exactly skims the surface of the water. We then consider the part of the object that lies below this water level, in other words, the part that lies below this plane that we've just been talking about, the plane of the water surface, and we refer to this part of the object as the submerged part of the object. Now, if the object is entirely submerged, in other words, if all of the object lies below the water surface, then the submerged part of the object is simply the whole object. And another clarification that I should make when talking about the submerged part of the object is this. If the object is in the shape of something like a boat, for example, then every bit of space beneath the water level that is not occupied by water because the object is in the way is still regarded as being part of the object for the purposes of how I'm framing Archimedes' principle, even though some of that space is not occupied by hard material, right? So, for example, one often hears that an object that is more dense than water must sink because of Archimedes' principle, but of course, a boat that is made of material much more dense than water can still float, and that's because the air occupying the capacity of the boat is, in effect, treated as being part of the boat for the purposes of applying Archimedes' principle. Of course, if the boat develops a leak, then you'll eventually have a consistent water level between the outside and the inside of the boat, and so the submerged part of the boat, from the perspective of Archimedes' principle, really will consist of just a part of the solid structure of the boat, and so if that is more dense than water, then the boat will sink. Okay, so now having defined the submerged part of the object, we can consider the volume of the submerged part of the object. So let's say, for example, that the submerged part of the object has a volume of 200 cubic centimeters, which is the same as 200 milliliters. We then ask, how much does 200 milliliters of water weigh? Well, 200 milliliters of water has a mass of 200 grams, in other words 0.2 kilograms, and so it has a weight of 0.2 kilograms force. And therefore, Archimedes' principle tells us that the upthrust force exerted by the water in the system on the object is 0.2 kilograms force. Now, when the object is an upright prism-shaped object, one can easily derive this correct version of Archimedes' principle from the hydrostatic pressure principle, as I've already mentioned, and I'll leave it as an exercise for you to do so if you would like to. But there is another simple, intuitive way to think about why we should expect Archimedes' principle to hold that is not restricted to prisms. Let's imagine replacing the submerged part of the object with just more of the same fluid, and at the same time, let's remove the non-submerged part of the object. So the fluid level, in other words, the height of the surface of the fluid, is the same as it was before, but now the horizontal fluid surface is uninterrupted by the object. Now, since the fluid surface lies entirely along a horizontal plane, what we have is a valid equilibrium configuration of fluid, and so, assuming that the system is in equilibrium, we can consider the balance of forces acting on the part of this body of fluid that replaced the submerged part of the object. Now, one of the forces acting on this part of the fluid is the weight of this part of the fluid acting downwards, and the other force acting on this part of the fluid is the upthrust force being exerted on it by the rest of the fluid. And since there is no acceleration of fluid, these two forces must balance out. In other words, the upthrust force being exerted on this part of the fluid by the rest of the fluid must act directly upwards with a magnitude equal to the weight of this part of the fluid. But now, the key point is that the rest of the fluid has no idea whether the entity that it's exerting its upthrust force on is more of the same fluid or some other object. And so, if we now return to the original setup, the upthrust force exerted by the fluid on the object is the same as if the submerged part of the object had been replaced by just more of the same fluid. So that's the underlying intuition behind Archimedes' principle, by which I mean, of course, the correct version of Archimedes' principle. Okay, so now that we've formulated our general statement of Archimedes' principle, we can now give the application to floating objects, and this is as follows. When an object is floating in a fluid, the mass of fluid that would fill the submerged volume of the object is equal to the mass of the object itself. Now, it's worth clarifying what the word floating actually means in this particular sentence. We say here that an object is floating in a fluid if the only vertical forces acting on the object are the object's weight and the upthrust force from the fluid, and these forces balance each other out. Now, for the rest of the video, I want to do two things. First, I want to talk briefly about the relationship between water level and submerged volume, and then I want to talk about how Archimedes' principle can be formulated in a way that is based on displaced fluid. So first, suppose I've got a container with fluid inside it, and with an object or collection of objects that are partially or wholly submerged in the fluid. Then the capacity of the container up to the fluid level, in other words, up to the level of the horizontal surface of the fluid, is equal to the volume of water in the container plus the total submerged volume of the objects. Now, the consequence of this is that for a fixed container and a fixed volume of fluid inside the container, specifying the total submerged volume is equivalent to specifying the fluid level. In other words, the geometry of the objects themselves plays no part in the relationship between the fluid level and the submerged volume. This relationship is entirely determined by just the container itself and the volume of fluid. And moreover, we can say more specifically that a larger total submerged volume guarantees a higher fluid level regardless of how the actual geometry of the submerged volume might be different. And a nice application of this is that it allows for a very simple and clean solution to a well-known classic Archimedes principle puzzle, and that is, suppose you're in a boat floating in a small lake and you're carrying a heavy rock and you throw the rock into the lake and it sinks to the bottom of the lake. How does the water level compare before and after you threw the rock into the lake? Well, I'll leave it as an exercise for you to think about. Okay, and now suppose we have a container with some fluid in it, but initially there is no object that is partially or wholly submerged in the fluid. And we make a note of the fluid level. And then an object is introduced that gets partially or wholly submerged in the fluid so that the fluid level rises. Now, the volume of fluid is the same before we introduced the object as after we introduced the object. And so this volume of fluid is still equal to the capacity of the container below the original fluid level. But after we've introduced the object, part of the capacity of the container below the original fluid level is now occupied by a part of the object, and therefore the volume of fluid that now lies above the original fluid level is equal to the volume of the part of the object lying below the original fluid level. Another way of thinking about it is this. Since the total volume of fluid doesn't change, the volume of space that was previously unoccupied by fluid but now is occupied by fluid is equal to the volume of space that previously was occupied by fluid but now is not occupied by fluid because it's occupied by a part of the object instead. Okay, now let's give a name to this volume. Let's call it VD. So in other words, in heuristic terms, Vd is the volume of fluid that has been forced, against gravity of course, to now occupy space previously not occupied by fluid in order to make way for the object now occupying some of the space that previously had been occupied by fluid. Now incidentally, if you were to ask me, in this scenario, what is the volume of the fluid that the object displaces? Surely the most natural way to interpret this question is as referring to this volume Vd. Of course, the weight of this volume of fluid, in other words, the weight of the part of the fluid that now lies above the original fluid level, is not necessarily equal to the upthrust force acting on the object. It will be less than the upthrust force unless the whole object lies below the original fluid level. Okay, well anyway, if we now add to both sides of our equation the volume of the part of the object that lies between the original fluid level and the new fluid level, what we get is the following equation. The capacity of the container between the original fluid level and the new fluid level is equal to the submerged volume of the object, meaning of course the volume of the part of the object lying below the new fluid level. Incidentally, another way that we could have derived this same equation is using our earlier equation that the capacity of the container up to the fluid level is equal to the volume of fluid plus the submerged volume, because this then means that the capacity of the container between the original and the new fluid level is equal to the change in submerged volume, but the submerged volume before the object was introduced was just 0. Anyway, let's also give a name to this volume. Let's call it Vs. So now, Archimedes' principle correctly formulated tells us that the upthrust force that the fluid is exerting on the object is equal to the weight of fluid that would occupy a volume of Vs. And note again that this volume Vs is greater than Vd by an amount exactly equal to the volume of the part of the object lying between the original and the new fluid level. And whereas Vd is equal to the volume of an actual part of the fluid in the system, namely the part lying above the original fluid level, Vs can be greater than the entire volume of actual fluid present in the system. So when we ask, what is the weight of fluid that would occupy a volume of Vs, we're not requiring that this fluid is a part of the actual body of fluid present in the system. Okay, and now let's talk about how Archimedes' principle can be formulated with reference to displaced fluid. Imagine we have a container that is initially filled to the brim with water. Now imagine that an object is gradually lowered into the water so that as water spills out of the container, the water level inside the container remains at the brim. Now, we can refer to the water that is no longer inside the container as being the displaced water. It's the part of the water in the system that is occupying space that previously had not been occupied by water in the system. Now, the key point to note about this setup is that it is infinitely fine-tuned so that all of the displaced water is now separated from the rest of the body of water such that it is not able to contribute to the water pressure and thus is not able to contribute to the upthrust force experienced by the object. And in this situation, the volume of the displaced water is equal to the volume of the submerged part of the object. Now, suppose we formulated Archimedes' principle as being a principle specifically about this infinitely fine-tuned scenario. Suppose we said, Archimedes' principle is the assertion that if an object is partially or wholly submerged in a fluid, and if
Throughout the submersion process, the fluid that is displaced from the original space occupied by fluid gets separated so that it does not contribute to the fluid pressure being applied on the object. Then, the upthrust force exerted on the object by the remaining non-displaced fluid is equal to the weight of the displaced fluid. Now, the physics in this statement is correct, and moreover, in principle, you can use this statement as a general statement of Archimedes' principle. You see, of course, in pretty much every scenario where you might have cause to apply Archimedes' principle, the displaced fluid will not be separated from the rest of the fluid, but nevertheless, you can always imagine an alternative history behind how your configuration of fluid and submerged object came to be, in such a way that this version of Archimedes' principle becomes applicable. In other words, any submerged volume can always be reimagined as a displaced fluid volume in an alternative history in which your original volume of fluid was equal to the sum of the actual volume of fluid that you really do have in your system, plus the submerged volume of the object. And so, I think there are some people who take this alternative history approach to interpreting the displaced fluid framing of Archimedes' principle. But unfortunately, what I think you're much more likely to encounter is the following. Someone gives, as the general statement of Archimedes' principle, that the upthrust force on an object is equal to the weight of the fluid displaced by the object, and there are no clarifications given that this displaced fluid refers to an alternative history involving more fluid than is actually present in the system. But what you do get provided is an illustration of this very example where all of the displaced fluid spills into a weighing device. And this illustration is provided for the purpose of helping to convey what is meant by the phrase the displaced fluid that appears in the supposedly general statement of Archimedes' principle. And so, in that scheme of exposition of Archimedes' principle, this illustration only has the effect of reinforcing the wrong intuition. It encourages the student to adopt the perspective that in general situations, the upthrust force experienced by an object is equal to the weight of the part of the fluid in the system that has had to make way for the object to descend into the fluid. And to help reinforce my point, let's now imagine that in our example here, extra height now gets added to the container, and while the object is forced to remain in exactly the same position, the displaced water that had spilled over is returned back into the container. So now, the displaced water does contribute to the water pressure. Please note that none of the rest of the fluid has moved at all during the process of returning the displaced fluid back into the container. So, in no sense have we increased the amount of the fluid present in the system that should be labelled displaced. But what we have increased is the water level, and hence the water pressure, and hence the upthrust force. More precisely, by Archimedes' principle as correctly formulated, the upthrust force increases by an amount exactly equal to the weight of water that would fill the volume of the part of the object lying between the previous and the new water level. By the way, please note that the geometry of the newly added part of the container affects how much the upthrust increases by when the displaced water is returned back into the container. If the added part had been narrower, then the same displaced water would reach a higher height, meaning that more of the object would be submerged, and hence the upthrust force on the object would be greater. And this ties nicely back to the hydrostatic paradox, where for a given volume of added water, the resulting increase in water pressure can vary greatly depending specifically and exclusively on the height that gets added to the water level by the addition of the water. Okay, well, I'll leave it there. Thank you very much for watching.